Everyone, I am Nishmika, final year IT in Webcoast Link Engineering College.
And I'm Mutlakshmi, final year IT in Wefcoast Link Engineering College.
Our guide is Mrs. M. Blessa Vinolin Pepsi, Assistant Professor, Selection Grade in the Department of Information Technology. Our project is a BERT-based smart contract vulnerability detection using hybrid secretary bed optimization. Our aim is to propose a novel smart contract vulnerability detection framework that employs transformers for contextual learning and efficient feature selection algorithm using hybrid secretary bed optimization to overcome efficiency and accuracy limitations for automatic feature learning. Our objectives are to develop an automated smart contract vulnerability detection model with feature extraction through BERT and to improve the performance of the model using hybrid secretary bed optimization. This is the overall flow of the model. It starts with data acquisition, where the dataset are the Ethereum smart contracts and the VNT smart contracts. The Ethereum smart contract consists of reentrancy, timestamp, ether strict equality, and dangerous delicate vulnerabilities. And the VSE dataset consists of the infinite loop vulnerabilities in the smart contracts. The next step is extracting contextual features from the smart contracts using BERT and then implementing a hybrid security bed optimization algorithm. And next features construction, which is the process of developing a low dimensional representation of smart contracts with the relationship between variables, functions, and patterns using contact graph and expert defined patterns. And then to improve the low dimensional contact graph and expert defined pattern features, the feature information for an efficient classification process, the feature interaction phase was created. This is the block diagram of the model. The raw solidity code of the smart contracts is the initial input. The tokenization is the initial process which separates the individual tokens, and then the embedding is applied to assign the location and its connection to other tokens, and followed by the process of extracting embedded features by the BERT encoder, and then selecting the features using hybrid secretary bed optimization, and then followed by the feature construction process which consists of contact graph and expert defined patterns, and then followed by feature instruction which consists of auto int and deep and cross network for interacting with the features, and then again in a feature selection for the extracted interaction features using hybrid secretary bed optimization, and finally the vulnerability classification is applied using a deep learning model multi-layer perceptron which uses a sigmoid function to classify whether the smart contract is vulnerable or not.
This is the models are present in our project. Tokenization, BERT, hybrid secretary word optimization, contract graph, expert knowledge pattern, AutoInt, and DCN MLB. The first step is the tokenization, is analysis of the solidity code. To do this, the code must be broken down into the number of fundamental units known as tokens. These tokens includes like operators, functions, literals, identifiers, and keywords. And then the embedding, the token from the tokenization stage are embedded using positional embedding and token embedding independently. The token embedding represent each token in the smart contract code as a 768 dimension vector. The output from the embedding layer is the sum of the token and the position embedding. And then the BERT, the multi-head attention mechanism determines the weighted sum of the input embeddings. It computes several attention heads in parallel. It consists of residual connection and the layer normalization and the feed-forward neural network.
The next process is hybrid secretary bed optimization. This technique selects the most relevant and eliminating features from the 768 dimensional feature vectors, reducing the dimensionality of the input data. And then this consists of strategies which are categorized into two groups: camouflage by environment and fly or run away. This is the contact graph module where the smart contract code is represented as a graph. These are the deep learning models present in our project: AutoInt, DCN, multi-layer perceptron. This is the dataset present in our project. It consists of two datasets: Ethereum smart contract dataset and VNT smart contract dataset. The accuracy comparison for different fitness functions are given below. Among the three fitness functions used here, the Rosenberg fitness function performs well for detecting vulnerabilities. This is the parameter comparison for timestamp data, where SL equal to 0.5 and J equal to 2 and R2 equal to 0.1 provides a high accuracy in determining the vulnerabilities. This is the tokenization output, where each file consists of a token index, the type of the token, and the name of the token and the position of the token. This is the overall test accuracy for reentrancy vulnerability dataset, which provides a high accuracy of 100%. The timestamp dataset provides accuracy of 0.9877. The infinite loop provides accuracy of 100%. Dangerous delegate provides accuracy of 92.63%. And then ether strict equality provides a test accuracy of 97.54%. And this is the overall comparison of accuracy of our proposed work with the comparing with the previous traditional models, where our proposed work provides higher accuracy compared to other models. This is the comparison of area under curve. Here the proposed work performs well compared to other models. This is the ROC curve analysis. This is the execution time analysis, where our proposed work executes with a lower time complexity and execution time compared to other models. This is the implementation of our project. This is BERT and transformer algorithm. It processes different files. This is hybrid secretary bed optimization algorithm. To select the optimal features, this is MLP classification for vulnerability detection. It provides high accuracy than other models. It calculates time and space complexity with test accuracy rates. Thank you.